Thanks very much, Will. That's a very kind introduction. I wish I could. I'll try to live up to it, but I think it will be impossible to live up to the introduction of somebody who knows all about greenhouse gases and steel. But thank you very much. So just to start off with, to give you a very quick intro to steel and greenhouse gas emissions, the steel sector emits around 3.7 gigatons of steel a year. That's around 7% of total global greenhouse gas emissions, about 9% of non-land use related emissions. So a big chunk of greenhouse gas emissions from steel. The graph I'm just showing you shows the emissions from around 300 representative steelmaking sites around the world. And that's using data from the CRU steel cost model. What it's showing on the x-axis is the proportion of carbon used, the proportion of scrap used as an input material compared to the proportion of iron ore used as an input material. And on the y-axis, you've got the greenhouse gas emissions intensity, so carbon dioxide equivalent emissions per ton of steel produced. On the left, you've got high iron ore making for steel, up to 100% iron ore. On the right, you've got up to 100% scrap metal. A few key things that graph is showing you. It takes 4 or 5 times as much energy to make steel from iron ore than it does to make steel from scrap, when you've already taken the oxygen off the iron oxide. So the GHG emissions on that graph are reflecting 3 things. They're showing very largely, as you can see from that regression line, the proportion of scrap used as an input material. It's also showing the source of energy used, and it's showing the efficiency of production. And the data here is scope 1, scope 2, and scope 3. So it's showing the efficiency of production from mine to metal. That showed us where things are today. In 2019, that's 2019 data. This next graph shows us where we need to be in the near future to achieve net zero. And to give a rough translation with a lot of nuances, but net zero steel making by 2050 is equivalent, roughly speaking, to a 1.5 degree scenario with all sorts of ifs and buts. To achieve net zero by 2050, all scope 2 emissions have to be net zero. Scrap use has to be maximized. The steel making from iron ore has to be using hydrogen, biocarbon, or direct electrolysis rather than coal as at present, or natural gas. Remaining emissions have to be captured and stored, and any residual emissions need to be offset to achieve net zero. Now that's an extraordinary challenge for the steel sector, and we need to get there as fast as we can. I mentioned that the emissions from scrap are about 1/5 of the emissions from energy requirement for making steel from iron ore. So the obvious question is, well, why not just use scrap to make steel? And if that were the case, and it was so simple, one might wonder why steel is considered to be a hard to abate sector at all. The problem is that around 84% of available scrap is already recycled. It also takes a long time, once you've made steel, for that steel to become available for recycling, as you all know, around 30 to 40 years, average life expectancy for steel in buildings, and maybe 12 to 15 years in cars. In infrastructure, it can be a lot longer. So scrap is essentially a limited resource, and most of the available scrap is already being recycled. In that case, why not reduce demand for steel and then try and meet the reduced demand using scrap metal? The challenge there is that projections for future steel use show either an increase or essentially the same kind of total demand for steel in 2050 as there is today. There are different factors contributing to that. There's population growth, and the world's population is projected to increase over that time period. And also, there's the expectation of further development, increasing development needs. In the US and somewhat less in Europe, the average steel stock per person, per capita in the population, is over 10 tons of steel per person. In India, it's around 0.4 tons per person, and in Nigeria, around 0.1 tons per person. And that's where the population is projected to increase, and where there's greatest need for increases, improvements in development. Set against that projected increase, and if that was all you would be thinking of, you would expect steel demand to increase. There's the likelihood of increased steel efficiency, using less steel to do more and replacing steel with other materials. Now, projections by the IEA with their sustainable development scenario show those factors approximately balancing out, so that total demand for steel in 2050 is projected to be approximately the same as today. In terms of scrap, the more primary metal that goes into the stock, the greater the opportunity for using scrap. So the proportion of scrap used goes up somewhat, but not massively, to around 55% by 2050, but certainly not enough scrap to meet projected demand, even in that sustainable development scenario. To add to that, the emissions from making steel from iron ore are so much greater, so that when you look at the total emissions over that time period, from now until 2050, you're looking at 80%, 90% of emissions coming from iron ore. So then the challenge is how to reduce the GHG emissions to steel. And again, there's a simple possibility. Why not just specify low embodied carbon steel? Again, it seems pretty obvious, and then let market forces work their magic. The problem is that the quickest and easiest way for a steel maker to make low carbon steel to meet a simple threshold is to use more scrap. So specifying low carbon, a simple sort of horizontal threshold for low carbon intensity for steel, essentially means you're asking steel makers to put more scrap into the steel. And as we have seen, scrap is a limited resource, availability is limited. So the outcome of doing that, not entirely and making things a little bit black and white, but basically the outcome of that is to move scrap around from GHG sensitive markets and users to GHG insensitive markets and users. And the world's most inefficient producer of steel, using coal-fired power to make steel from 100% scrap, still has lower emissions than the world's most efficient producer of steel using state-of-the-art technology to produce steel from 90% iron ore. So we're not really addressing the problem. And we can play around with those thresholds. We can set different thresholds for different technologies. We can have a high threshold for blast furnace, basic oxygen furnace steelmaking on the left, have a lower threshold for electric arc furnace steelmaking on the right. But you can vary the proportion of scrap from blast furnace, oxygen furnace steelmaking from 10%, less than 10%, up to maybe 30%, 40%. So again, however you play around with those thresholds, you're not solving the problem. The case remains that the more scrap you use, the lower the emissions. We keep coming back to that problem. So is there a better way of doing this? Well, it would be a less interesting presentation if I thought the answer were no. And actually, I think the answer is pretty straightforward, that there is a better way, and it's to specify performance levels that are normalized for scrap use. And that approach is technology independent. It doesn't depend on you knowing whether it's an EAF, an electric arc furnace producer, or a blast furnace producer, or any of the new technologies coming online. You just need to know the proportion of scrap to iron ore being used as the input material. It rewards lower scope 2 emissions. It rewards greenhouse gas emissions efficiency from mine to metal, and it incentivizes performance for all steel production, high iron ore based production, as well as high scrap based production. And in doing so, it incentivizes investment in new technologies for high iron ore based steel making, which is the real $1 trillion challenge for the steel sector. And that's what my main work for the last 12 to 18 months for Responsible Steel has been, trying to work out how to do that. there is certainly plenty of devil in the detail. We need to agree rules for scope boundaries for scope 1, scope 2, and scope 3. We need internationally consistent rules for measuring greenhouse gas emissions, which don't currently exist. We need to define these emissions in terms of site level crude steel GHG emissions intensity. And what we are proposing at Responsible Steel is to define 3 different performance levels. A basic performance level, which asks, is a steelmaker better or worse than average, given the amount of scrap or iron ore that's being used? And then 2 further levels to ensure that there are incentives for the leaders, as well as, if you like, the better than average performers. And those at the moment are being proposed to be set at a lower embodied carbon level, and then at a near zero embodied carbon level, allowing specifiers to be forward-looking in terms of setting their specifications and their own targets. And then finally, just to say that this approach is not intended to be a replacement for, an alternative to, caring about the embodied carbon emissions of products. It's intended to complement that, not replace it. Steel users can and should specify the lowest embodied carbon for a product, given the performance level, given whether the performance level is just below threshold or one of those more demanding threshold levels. So it's complementing existing data from EPDs, not intended to replace it. We need both of those things. A performance level for the site's GHG emissions intensity for making crude steel at the site level, together with the existing EPD data, which gives you the embodied carbon for the product. I'll stop there and very much welcome any questions afterwards. And thank you very much.
Thank you, Matthew. Absolute whirlwind tour, but I think really, really important. And there's some really big facts in there about sensitive emissions due to iron ore between now and 2050 that I think was just worth hearing from somebody who knows about this stuff. So thank you. Do please, if you're listening, please put questions in the chat, but we will then bring ourselves back to the questions in about half an hour time after we've heard from our next 2 speakers. So now I am really pleased to be able to introduce Paul Palassel. Paul, as well as being an associate at Ramboll and a practice structure engineer, he also sits on the low carbon concrete group, which I think, if I'm right, sits under the Green Construction Board here in the UK, who we've asked to basically give a similar sort of view of the world of concrete to what you just heard from Matthew about steel. And I have a sneaking suspicion there's going to be a bit of overlap in terms of the approach taken to dealing with such a tricky issue, but I'll let Paul tell you more. Over to you, Paul.
Thanks, Will. Yeah, my presentation is a bit different to Matthew's, but hopefully will be as informative. As Will says, I'm part of a large group called Low Carbon Concrete Group, who are trying to work out a route map to bring down the carbon intensity of concrete as a material. So I'm going to run through a few different aspects of that now. So I'm going to talk about how much carbon there is in concrete, where it is in the concrete, what you can do about it, and a quick wrap up at the end. So first of all then, how much carbon are we talking about? And I've got this slide here, which ideally I would give you a bit of time, but will not let me do that. So you've got a few seconds pretty much to have a look at these different proportionately sized circles of 5 common building materials. And this is kilograms of CO2 equivalent per kilogram of material. And I just thought it'd be interesting for you to have a think about which of those might be concrete. There's a hint which of the colors are deceptive on purpose, but I'll cut to the chase. And actually in this context where we've got CLT without sequestration, before anyone comments, rock wool, steel, plasterboard and concrete, you can see concrete is actually the lowest per kilogram. So, in terms of a material per kilogram, it's quite low, which is a good thing really generally. However, obviously the way we use it, we just use so much of it that in its actual application, it becomes the biggest once you start looking at how much we use per square meter. And so this is the challenge we've got to face, and this is sort of typical 100, 150 kilograms of CO2 per meter squared for a building structure. Going into a bit more detail then about what kind of carbon you might expect to see in concrete and reinforced concrete. This is the sort of typical range you could expect at the moment, anywhere from 125 to 375 kilograms of CO2 per meter cubed. I've used meters cubed here because we tend to specify concrete by the cube. It just gets a bit confusing, but that's the right kind of order. And then obviously rebar is around 0.84. I think that's similar to the number that Will has in the carbon guide from the I/D. And so what that gives you is approximately 184 to 500 and something kilograms per meter cubed for reinforced concrete, which is a pretty big number and a factor of 3 from the lower sort of strength to the upper strength. So you can see it's pretty significant, really. It's a big quantity of carbon. So I think that's the sort of number you should take away, really, is that, for unreinforced concrete, you're around 300-ish. And then when you reinforce it, you could be as high as 450, 500. And that's A1 to A3. That's just leaving the factory or the batching plant. I did come across this quote recently in National Geographic, which I thought was quite interesting, which said that hour for hour, there is just about nothing you as an individual can do that's worse for the health of the planet than to sit on an airplane. Airplane is American, but I thought probably not if you're a structural engineer. So if you think about the sort of amount of carbon we can control in our daily jobs per hour, it's actually far bigger than that. And to give you some context, a meter cube of concrete, unreinforced, is similar to the amount of carbon associated with a return flight from London to Copenhagen. So, what's that, 2-3 hours journey? So could you save a meter cube of concrete in a couple of hours? I mean, it's probably just the difference between specifying 50 mil, 75 mil blinding or none. I could save far more than that. So just want to bear in mind in the context of what we do. So where is the carbon then? Well, hopefully most of you are familiar with what goes into concrete. We've got sand and gravel, water, cement and steel. There's also admixtures, which I haven't shown, but they can also play a significant role. And if we look at how they are put together, the distribution of those materials by weight, then the vast majority of the weight of concrete is in the aggregates, the sands and the gravels, 70 to 80% or even higher sometimes. The cement accounts for 10 to 15%, perhaps 12% in this example, could be a bit higher as well. Water, steel, and you can kind of just see a slither which represents these other materials, which can have an important role as well. So that's the distribution of those materials by weight. But if we look at the distribution by embodied carbon, it's a different picture. And all of a sudden we can see how significant cement is, which completely dominates the embodied carbon in concrete, and then followed by the steel. The aggregate itself is relatively trivial in this context. That's not to say aggregate's not important, and there are other aspects of aggregates and how we use those that need to be considered. But in terms of carbon, it's the cement and the steel that are the most important thing. Admixtures do start to make an appearance there as well at this point, but again, it's still relatively small, not worth focusing on at the moment. It's the cement and the steel. And just as a bit of a wrap up, in terms of cement and how we use it in the UK, we use around 11.7 million tons or consume 11.7 million tons of cement in the UK, which is about 10 million tons of CO2, which is about 1.4% of the UK's territorial emissions. I think that was. No, that's not. That's consumption emissions. So not as big as the world sort of average, but still, a significant number nonetheless. And that gets turned into a mixture of ready mixed concrete and then other cement-based products. And that's also not to be, discounted, because actually about 50% of cement goes into mortars and architectural items and all kinds of other things as well. But we tend to focus on the ready mixed concrete aspect of it. And this is 22.5 million cubic meters. So again, a huge number, about 0.3 cubic meters per person in the UK. So a huge amount of concrete. So that was a very quick canter. I'm having to go fast because I'm scared. I can see Will looking at me. that's a quick canter through the numbers, where the carbon is in concrete and how much we're talking about, but let's talk about what you can do. So I know this is a bit of a broken record, but clearly the first thing we need to do is use less. And there's some really fantastic guidance that has been assembled in the past couple of years on this about how you can, just change your grids and look at loads and efficiency, and you can shave, massive amounts of material out of any structure, but certainly out of a concrete structure. So that's really important. But also what's important is helping others to use less. And what I mean by that is working with contractors and other sort of subcontractors to really help them to make sure they also don't go a bit cavalier with this sort of temporary works. I've got a huge project in London at the moment, and I'm astonished at the amount of concrete we're using in the temporary works, in some cases being ripped out again within weeks. So are there things that we can do as designers and engineers that can perhaps remove the need for some of these bits of concrete? I mean, if those of you who've been to site, you probably will have seen hoarding that goes up for 2 years, and quite commonly a big lump of concrete is used as the ballast, and that's every, I don't know, 5 meters. And it's not necessarily a big piece by itself, but it's just a completely wasted lump of concrete being used as ballast. So let's try and work with our supply chain to help them understand how they can make savings as well. And of course, let's talk to our colleagues in building services and architecture, work with them. Other things we can do differently together to try and reduce the amount of concrete we use, or indeed, from an architectural point of view, the amount of concrete they might use in architectural finishes as well. But if you are going to use it, and I'm sure that's why you're here, then we need to optimize it, and that means optimizing the carbon. And not to contradict myself, but that doesn't necessarily just mean use the absolute minimum amount of concrete. It means use the minimum amount of carbon in that concrete system. So you've already tried to avoid using it in the first place, but this is now, okay, I'm going to use it. What's the best balance of concrete strength, etc., and steel to get a low carbon solution? So that's what I'm going to take you through in a bit more detail in the next few slides. So targeting the cement then, the carbon intensity of cement is essentially 2 components we need to consider. One is cement type and the other is cement content. So we consider cement type. Many of you will be familiar with Portland cement, CEM1. We also have a whole range of other types of blended cements which are in the codes now and you can always use. So Portland composite cements, those using blast furnace, pozzolanic, etc. And some of you will be aware of alkali activated cements like CEM3 or geopolymers like earth-friendly concrete as well, which are not in BS 8500, but are also starting to be used in the UK through a different route. But something to be aware of here is that the vast majority of these blended cements use ground granulated blast furnace slag as a way in which to bring down that carbon intensity, because GGBS has about 1/10 of the embodied carbon of Portland cement, which is great. It's good to bring those down. But we need to be cautious here because actually globally, and this is a global problem, we use around 4,000 million tons of cement per annum, and we only produce around 10% of that in slag, possibly less as we move forward as well. So clearly, we're not going to be able to substitute cement for the sort of rates that you may have seen on projects or heard about, 18, 19, 95%. We're not going to be able to do that for a long time, or indeed across all of our projects. And so we need to find solutions which not only use GGBS, but perhaps use it blended with something else, or try and find a different alternative material as well. And in the next year, you're going to see a greater range of blended cements in BS 8500. So the key message here is really to try and see if you can use a greater range. And that's about talking to your suppliers, what they've got available, and supporting those new cements wherever possible. Because this solution is not going to be a simple case of taking one thing and replacing it with another. The reality is we're probably all going to have to learn about different types of cements and using different blends whenever possible. The 2 sort of big candidates, I think, which we'll probably hear more about in the near future, are calcined clays and also using a far greater proportion of limestone filler, both of which meet the sort of test for being available everywhere and are relatively cheap and abundant. So providing we can develop that, that could be a significant step forwards. So that was cement type, but then we've got to think about cement content. And this is a real winner actually, because, just bringing down the cement content is just a saving. That's what we want to focus on. We haven't got to come up with any new material, we just bring down the content. And in terms of what influences that content, this is my assessment, so don't take this as definite, but I would suggest that perhaps 60-70% of it is down to designers, so things like durability, design strength, cement type. Of course, that also plays a role in cement content. And then the other part of it is down to construction and supply drivers. And this is really important and often overlooked, because actually you may specify a concrete with a super low strength and think you're fantastic and it's going to be great. But when it gets to site, because the way they've got to build it, they've got to add in huge amounts of cement to actually make this concrete workable. So that's something that happens already all the time. You see concretes that have huge amounts of cement in them, which actually would give you a really strong cement, but it's rated much lower because that was the design at the time. So this is something we've really got to tackle. To give you a couple of examples, this is some data from Ramble projects that I collated over the last, these are about 90 mixes over the last 5 years. And this is the range in content you can see, and against the strength on the bottom. And you can see that even though the strength here has only gone up by, I think, something like 7 or 8 newtons per millimeter squared, we've got a doubling of cement content. Now, there are other reasons for this, don't get me wrong, and there's durability and things like that, but it doesn't justify that kind of distribution, in my view. And if you look at then embodied carbon, it gets even worse because it spreads out more because of the cement type aspect as well. And you can see this enormous range now, sort of factor of 3.5, 4, between that sort of C25 and a C32, and that just doesn't seem right. So what we need to try and do is to compress this down and find out why was it that that cement on the left was able to have such a low cement content and embodied carbon consequently, and the one on the right had such a large one, and what can we do to try and bring it down, bring the average down? Because all these cements, these are just normal BS 8500 cements, nothing new or novel here. This is just regular engineering. So the approach that I'd like you to all take, and the key deliverable that we're working on in the low carbon concrete group, is this route map, which is going to be launched soon. I don't give a date in case I get it wrong, but soon, in the next few months. One of the key aspects of it is going to be this flow diagram, and there's many other different bits of guidance, but one thing I want to draw your attention to is this idea of a systematic approach to your project and how to bring down that carbon and optimize your concrete for carbon. And it really starts at the beginning. So you're thinking about durability, reinforcement, minimum cement content. You work your way through. I can't go through all this in detail, but I really encourage you to go through it. And ultimately, you'll find yourself in a position where you've got the best solution for your project. Just going to wrap up quickly. So the first thing to say is we use a lot of concrete. This is a given. It's governed by, the embodied carbon is governed by cement and steel. We need to use less first, of course, but let's also think about the designers and the construction end. When we are going to use concrete, we need to optimize it for carbon and on your project. So really think about your project. Every project will be different. Some will have lower carbon than others. That's just the way that it works, but let's really focus on your project and think about cement content, not just type. Be really flexible if you can with suppliers and explore the range of cements they might be able to give you, and maybe test them out. And as I say, look for BS 8500 next year, which has got more coming. Support new technology, and particularly things that use mixes that aren't just reliant on GGBS as the way to bring down the carbon. And perhaps most importantly, you've got to talk to each other. So collaborate with clients, contractors, suppliers, and designers, and hopefully we can find the right solution. Thank you.
Thank you, Paul. Some really wise words there at the end. I think, if there was one key message from all of that, it's how you use concrete being the absolute key. Really looking forward to seeing that flow diagram up here. Can't beat a good flow diagram, can you? Good. So we're now going to move on to Will Hawkins, who's going to talk to us about timber, sort of finish off our trio, as it were. And apologies to any brick enthusiasts in the room, but we just didn't have the space to fit in a fourth material. Will is a lecturer at the University of Bath, but was a practicing engineer prior to that, where he worked on a number of different projects around London. And we invited Will to speak really because he, I think, gave the clearest explanation to me of sequestration in timber when I first started asking people about this topic a year and a half or so ago. So I'm hoping that he can distill some clarity and wisdom to you all as well as he managed to do to me back then. Over to you, Will.
Thanks very much, Will. No pressure then. It's not a particularly clear subject, but I'll do my best. Okay, so I guess you can see my screen and you can hear me, so I'll crack on. Okay, so I guess the really exciting thing about timber that we hear about is that, unlike other structural materials, it has this benefit of carbon storage and sequestration. And that's led to this big, exciting idea that buildings can become a carbon sink and can have climate benefits rather than just being negative. So that's kind of been around for a little while now. This is a paper in Nature Sustainability, which has had a big impact. We've started to see this idea talked about in the mainstream media as well. It's been picked up by the UK government, who are now asking us to rapidly scale up the levels of wood used in construction. And it's also being used, this idea, on project level. So here's a recent article in Design. The Serpentine Pavilion, their use of biomaterials more than compensates for concrete emissions. So brilliant. I mean, this is a really exciting idea, but, you know, and I think it's very positive, but I think, you know, there's more to it. And is it true that more timber means less carbon? That's what I'm going to be discussing today. That's what I've been thinking about for the last couple of years. So to answer this, we need to talk about different types of embodied carbon. So on the first hand, we have fossil carbon, and that is CO2 released from permanent stores, such as fossil fuels through combustion or limestone through calcination. And on the other side, we have biogenic carbon, which is CO2 stored in bio-based materials, including plants, which is sequestered through photosynthesis and released through combustion or decomposition as part of a carbon cycle. And unlike other structural materials, timber and natural plant-based materials have both, which is where this kind of complexity and where this discussion comes from. So let's think about the life cycle history over modules A, B, C, and D, which hopefully you'll be familiar with, in terms of fossil and biogenic carbon emissions for timber. So in module A, there's plenty happening that emits fossil emissions when we produce timber structures. So there's forestry operations, harvesting, transporting the logs, limbing and debarking, sawing, kiln drying if we're using a fossil fuel to power that kiln, any product-specific processes, and producing adhesives, surface treatments, fire-resisting treatments, things like that. And so that all adds up to quite a lot of carbon that we can see here in module A. As a quick aside, this is just some data from the ICE database that compares the module A1 to 3 fossil emissions for different types of timber materials. And as a rule, we can say that the more processing and more adhesives we use, the higher those emissions are going to be. I should stress that between different producers of the same types of material, we also see a really big variation. Often that comes down to how they're firing their kiln. Okay, and in module A4 and 5, we also have transportation to site, prefabrication, on-site activities, and any wasted temporary materials, as we do for anything else. Now for timber, those module A4 emissions can be quite large, and they can be a little bit counterintuitive as well. So in the UK, we're often sourcing our timber from Scandinavia. We might think that sourcing it from the UK might be better, but if we do a quick calculation to compare transportation of 1 kilogram of timber from Scotland to London, we have this much CO2 per kilogram by road. We might compare that to somewhere in the middle of Sweden that gets to us via train and then ship and then a little bit of road, and it can actually be half as much. So it's quite important, particularly with timber, to know where it's coming from and how it's getting to you, because those A4 emissions can be quite large, because often the timber is being produced a long way from where it's being used. So just something to keep in mind. Okay, so that's module A, fossil emissions. We also have biogenic emissions in module A, and that's because sequestered carbon is entering our product system. If our kilns are fueled by offcuts or sawdust, then that ends up being carbon neutral. And in terms of on-site activities, if we have temporary works, the biogenic carbon will self-cancel, because that carbon is coming into our system and leaving it when that gets disposed of. So overall, we have a negative biogenic emission in module A. In module B, not much happens. We have any fossil emissions to do with replacing, repairing and refurbishing. And similarly with the biogenic emissions, a like-for-like replacement will be self-cancelling in terms of biogenic carbon. And then we get to module C. As for anything else, we have deconstruction, demolition, transportation of waste, and waste processing, which for timber typically involves either incineration for energy, recycling, or landfill. So that gives us a bit of fossil emissions. This is some data from Edinburgh Napier University that looks at waste timber. Again, this is in the UK. Sorry, this is quite UK focused. just realized I haven't started my timer. Okay, there we go, 15 minutes from now. The key things to take away from this is that half of our timber waste is coming from the construction industry. So either directly from construction sites or from demolition. And most of it is going into biomass energy where it's being burnt to produce electricity. So that CO2 is being re-released, the biogenic CO2. Otherwise, it's being recycled, or more accurately, downcycled into mostly chipboard, but also animal bedding and MDF. A very small amount of it is being landfilled. So when it comes to biogenic emissions, in module D, in biogenic emissions, they're all leaving the product system there, no matter what happens. Sometimes they're not going straight into the atmosphere, sometimes they're being recycled, but typically that's a short-lived product where it's going to end up back in the atmosphere. We shouldn't forget module D, of course. If we're incinerating to create energy, to create electricity, we're avoiding grid electricity. And if we're recycling, we're avoiding some A1 to 3 production as well. So we have negative fossil emissions in module D, and we have negative or a re-emission of the biogenic carbon. So we end up with a graph that looks something like this, where our net, over the full life cycle, we have a net positive fossil emissions and neutral biogenic emissions. Okay, so how does that get dealt with in terms of environmental product declarations? So this document here, BSEN 15804, is the guideline or the standard that governs the production of environmental product declarations. It has quite a lot to say about biogenic carbon. So it describes this as accounting for biomass CO2 transfer to or from any non-native forest. So that would typically include a plantation where most timber would come from that we'd be using. Any other product system, so if you're using recycled timber or if your timber becomes recycled at end of life, that's a biogenic carbon transfer, or emissions to air from combustion or degradation. It tells you to report biogenic carbon separately to fossil carbon. If you use timber without replanting, that incurs a heavy penalty due to land use change emissions. The EPDs for products containing biogenic carbon must always include modules C and D. So what they're getting at here is they want that cancellation to happen, and they're really explicit about it in this document. The quantity of biogenic carbon is that within the product, so not including the forest or the trees, just what enters the product system itself. The permanent biogenic carbon storage cannot be included. So at end of life, it has to leave the system again. And any effects of temporary biogenic carbon storage cannot be included either. So this is the 2019 version of this document. So any EPDs to do with timber that you see from 2019 onwards should comply to these set of rules. Now, this does seem a little bit harsh because, you know, that carbon is being stored in our building or in our product, but this document is saying that we actually can't account for it. So how does that stack up against the reality, or a different way of thinking about carbon storage in forests and products? So this image is borrowed from an analysis by the Forestry Commission, and it shows the amount of carbon stored in a forest over a certain lifetime over various crop rotations. So we have the soil, debris and litter, the trees themselves, and you can see that in between different rotations, in this case it's a 50-year rotation period, we have increasing in forest carbon, which then reduces and goes up and down again with a similar peak between cycles. What we can do is this brown color here represents the accumulation of products being made from that forest, which may accumulate over time, particularly if they're long-lived products such as carbon stored in a timber structure. This dotted line for comparison is a forest if we just left it alone. So you can imagine if we can accumulate enough forest products, we could go up above this line. So how can you account for carbon storage? If the codes say that you can't in an EPD, but we know that there are some benefits to carbon storage, how can you account for that in your, when you're communicating your designs or when you're comparing designs? So I think storing biogenic carbon in buildings does have climate benefits. How can we communicate it? So the easiest thing you can do is to just report biogenic carbon separately alongside fossil carbon, making it clear that that biogenic carbon is part of a short-lived cycle. So it's inherently different to fossil carbon, which stays in the atmosphere forever. The the biogenic carbon is temporary, but it's a benefit. So you can think of it in terms of a carbon handprint, and you can just report it separately. Something else you could do is show that temporary storage graphically. So this is a graph of storage over time. So one thing you might do is to choose this instantaneous approach, where in module A, you have the biogenic carbon going in, and in module C, you have the biogenic carbon going out. That's looking at your product system in isolation. There are, however, other approaches. The backwards looking approach goes back to when the tree was planted and models the growth curve of that tree, and before getting back to re-release of module C. Or there's a forward-looking approach which starts at 0 and then modules the reabsorption from a tree that was planted to replace the one that you harvested yourself. So if you apply this to a project, it might look something like this on the right. This is a study that I published recently comparing concrete, steel and timber based on the Bureau-Happold structural sensitivity study published by the IStructD. So you can see that if I'm using the forwards-looking approach, then we have our fossil emissions, we have our sequestration, and then we have our re-emission at end of life. Now, personally, I like the forward-looking approach for a number of reasons. Firstly, because it starts at 0. So when your project is being conceived, you're not already accounting for a negative emission for something that happened 50 years ago. It really nicely distinguishes between fossil and biogenic emissions. So here you can see them quite clearly separated. And it also rewards you for using a faster growing species, which naturally is going to be absorbing that carbon more quickly. And you can see that visually in the forward-looking approach. If we're using something like hemp or straw, it's going to reabsorb that carbon really quickly compared to something like oak, which is going to take a while to get that benefit. Thirdly, if you want to take this further, you can try and answer the question of what that temporary storage does in terms of the climate using something called a dynamic life cycle assessment. I won't go into detail. Again, you can follow this publication here. But essentially what you can do is you can see what happens in the climate in terms of the mass of CO2 and how that decays, and even work out what the temperature change over time is going to be when you've decided what your approach to carbon timing is. Okay, so I've spoken a lot about carbon there, but I think there's also a wider perspective to talk about. So in the EU, the total area of forest has gone up 9% since 1990. Roundwood production has gone up 40%, and the growing stock has gone up 50%. 73% of the annual increment is harvested, which means we're not at, so it means that so that's how the carbon is accumulating every year, because we're not quite harvesting as much as is growing. So this is all very good news. However, 33% of the forest area is single species. So as you can see in this image on the right, this is where most of our timber that we're using structurally is being produced in monoculture plantations. And unfortunately, they're worse than multi-species plantations in terms of biodiversity, soil health, pest, fire and wind resistance, and recreation. Other evidence shows that there's an inverse relationship between biomass production and biodiversity conservation. So if we were using less timber, it might be that we could have nicer, more productive and more biodiverse forests. I should mention as well, we talk about this in terms of timber all the time. We don't often talk about the biodiversity impacts of concrete and steel. So this is a big steel production plant, and this is a limestone quarry. Neither of those are particularly biodiverse either. So I just want to say that too. Okay, so what about future supply and demand for timber? Again, this is another big question that comes up. If we want to use more timber in construction, where's it going to come from? Is there going to be enough? So this study, produced by the think tank Material Economics, suggests that current decarbonisation plans will use 40 to 100% more biomass than will be available in 2050. Now that's largely due to power generation, but increased use in construction is also part of that. So there is a worry there that we're not going to be able to sustainably supply all of the timber that we need based on our 2050 carbon commitments, which include more timber in construction and which also include more fuel for biomass. On a global level, the World Bank have come to a similar conclusion. They predict that demand for global industrial roundwoods will quadruple by 2050. That's going to outstrip supply, and that risks fueling unsustainable and illegal timber flows. So there is widespread concern that we're going to be using more timber than is going to be available despite the fact that we're seeing increases in the amount of forest coverage and forest production in the Northern Hemisphere. If we're looking at what's happening right now, according to the TTF's member survey earlier this year, demand for timber products is at an all-time high. And as I'm sure many of you are aware, the price of imported wood into the UK, which the majority of our wood is imported, has really, really shot up recently. So we're already starting to see increased prices. And, you know, if demand continues to outstrip supply, obviously this isn't just a supply thing, there's also Brexit involved in this as well, and COVID. But this could be a shape of things to come. Okay, so just to summarize, with some principles for design and specification of timber. First of all, know your material. So as a minimum, you should be sourcing your timber from sustainably certified forests, by the Forest Stewardship Council, for example. That's the bare minimum you should be doing. Generally, that implies that your forests are going to be renewed and there's going to be no harm to the ecological systems, although that also is questionable. There's some evidence that that isn't always the case. So I'll leave you to check those out. Even better is to trace and investigate your supply yourself. So find out where your timber is coming from, what's the rotation period, where is it, and how far is it being transported, and what are the local forestry practices. I came across this brilliant website the other day called Global Forest Watch, where you can actually see all over the world what, you know, how is that forest being managed, what's being cut down, what's being grown every year. Really interesting to have a look at. The second key principle is to delay the re-release of biogenic carbon. You can do that in a number of ways. Firstly, by reusing timber destined for recycling, incineration, or landfill. That might be some local floorboards that you can get hold of, or it might be a whole existing timber structure. You could divert low-value timber into structures. So this is an example from Hook Park, where they've taken small diameter roundwood and built a fantastic structure out of it. That timber would have likely otherwise been burnt. You should always maximize the lifespan and design your timber structures to last a long time, and design components so that they can be reused in future. And finally, design lean. So why should we design lean? Well, we're going to minimize module A fossil emissions, which are going to be dominant and permanent. We're going to reduce costs, which makes timber more likely to be used over potentially more carbon intensive steel and concrete alternatives. It reduces pressure on land and biodiversity, and it enables a valuable but finite resource to be shared more widely, so we can make more timber buildings if we use less. So in summary, more buildings in timber, less timber in buildings. Thank you very much.
Thank you, Will. And we should probably credit Jane Anderson with the quotes, seeing as I think she says
Yes.
it more than anyone else. So even if she didn't invent it, she certainly says it the most. No, thank you for taking us through that. We're going to go on to Q&A now. And we've actually got 20 minutes because we figured that we'd probably need a bit longer than usual, given the amount of detail that we'd asked the three speakers to go to. And judging by the number of questions that have come from the chat, I'm sort of wishing we set aside about an hour and a half for this, but there we go. We'll do what we can in 20 minutes. I'm deliberately going to start with Matthew so we can get back to steel, given that it's been the longest since we heard you speak. And we'll try and group things together a bit if we can. So we had a couple of questions, Matthew, which kind of lead towards the slightly wider question. What should practicing structural engineers do with the sort of stuff you're presenting on? So, you know, you mentioned your normalized threshold limit. Is that curve available to people? Do you recommend that they could try and use it now in their material specs? So, any thoughts on that?
Thanks very much. I think I mentioned that the devil is in the detail. To use those curves, you've got to know that anybody plotting where they are against the curve, they're measuring their carbon in the same way. It's got to be consistently measured using exactly the same rules wherever you are in the world. So there's quite a lot of devil in that detail. And also I mentioned that it's scope 1, scope 2, and scope 3. So for example, with the upstream materials, you need to know that they're including the same upstream materials. They're not sort of cancelling out pig iron or something, which would make a massive difference. You've also got to be careful with things like, well, the definition of scrap and such like. So I suppose the simple answer is you need two pieces of data. You need the proportion of iron ore to scrap being used as an input material, but there's complexity there. And you need the GHG emissions intensity per ton of crude steel for the site, but there's an awful lot of complexity there. How do you wrap that up? I think the answer is you do need an international standard, and that's what Responsible Steel has been working on. There isn't one at the moment that will give you that consistency. I think the good news is we've been working on it. The slightly less good news is it's still a couple of months before it will be available. We're expecting to finalize, well, we've done the heavy lifting. We're now on our third draft. The heavy lifting will be done by the end of this year. And then there's a final process actually for ratification and approval of that standard. So I suppose the easiest thing would be wait until that's available. And then you'll be able to just ask, is this steel certified? Is it level 1, level 2, or level 3?
So yeah, okay. So it sounds like once you go live as a standard, it's something that plastic engineers can just simply refer to. Do you have any thoughts on, I mean, obviously, you know, if this goes live, let's say it goes live at the end of December, at the end of this year, does that mean that as of the start of January, engineers working on projects are likely to see Responsible Steel certified steel appearing on projects, or will there be a bit of a lag whilst suppliers sort of catch up?
I think there will be a bit of a lag. It was interesting listening to the presentation on timber and biodiversity. Responsible Steel doesn't just look at GHG emissions. I've been focusing on that. And actually, you could have talked about the biodiversity impact or the water impact of steel, and you could have looked upstream at the mining footprint. So Responsible Steel looks at a broad range of issues. Now, we've got steelmaking sites being certified. Already the first sites have been certified, but that's not covering these greenhouse gas emissions intensities yet. That's the further step, which obviously can only take place once the standard is finalized. I think it could be fairly quick for those steelmaking sites, they've got the data to determine whether or not they're above or below that threshold. But there's additional work on the input materials, I think, which will take a little bit longer to do. So optimistically, I think it would be the back end of next year before we will see the first Responsible Steel certified steel on the market, I would say.
And a final question on that, I guess, would be, so we had somebody ask it about cost. I mean, do you foresee that this is going to push up the cost of steel? Will Responsible Steel certified products cost more than ones which are not?
Well, there's no reason why Responsible Steel certified products should cost more, I think. Sort of the marginal cost of certification is really spare change. I mean, making low carbon steel, it will depend very much on how you're making steel. Making low or near zero or net zero carbon steel using high iron ore, certainly the projections are that's a more expensive way of making steel. If you're using, hydrogen reduction, for example, or direct electrolysis, that's certainly a more expensive way of making steel if there's no effective price for carbon. But that's sort of the longer term question. And if you're using EAF, for example, the price difference will be how much is your renewable energy costing fundamentally, and what are the costs around that. So I think that the way the world needs to move, there need to be a lot of policies put in place to allow the market basically to make low carbon steel financially more attractive than the high carbon version. That's where the world has to go. A lot of things have to be in place for that to happen. The Responsible Steel certification bit, I think, is almost a rounding error compared to, well, how do we make low carbon steel?
Yeah, that makes sense. Thank you. I'd like to open a couple of questions to Paul. I mean, a lot of this is sort of related, and it's to do with the practicalities of doing some of this stuff again. And the first question that sort of jumped out at me in the chat was one about persuading reluctant contractors to agree to cement replacements. And I've heard this a few times from other people as well in the past of, I've written it into my spec and the contractor's just come back and said, program and queuing time me, I can't, sorry, it's SEM 1 or nothing, Do you have any thoughts on that? Do you have any sort of comments on the arguments you might make in that scenario?
Yeah, I think it's a really good point. As you say, it does come up a lot. I would say the key thing is to have conversations as early as possible, first of all, and that includes getting the client on board if that's possible. Get them part of the discussion as well. I'm seeing that a lot of subcontractors now increasingly are actually want to do something. They want to do the right thing, and it's saying, okay, well, let's work around this. How can we do this with you? And I think rather than just accepting a blanket, we can't do that, I would go through every part, if possible, on the project and understand, well, why can't you do it here? What's going to happen over here? How about we focus on the foundations that don't have a strike time and, really maximize the potential there and perhaps have less potential elsewhere. I'd also say that get them to look at a copy of all the cube results for some of the other projects. And normally the strength you achieve is so much higher than it really needs to be. It's staggering. You know, some of these cubes hit their design strength in 3 days all the time. So clearly they probably could have a bit less cement in them. So it isn't going to be easy necessarily, but I think that, you know, just keep having the conversations. And if every time, if for the first 4 times someone says no, you know, the 5th time they might say yes, and then you can start to do it. But it's a bit of a mission, I think, you know, that we've got to have to take on.
Yeah, I agree. And I always say to people, the more we ask collectively as a group, the more normalized it becomes. And then the more likely you're to find that people just turn around and say yes, because they're sick of hearing it and think they might as well give it a shot. We've had a question about the guide, actually, or the sort of roadmap that you talked about, the low carbon concrete group guide that's coming out. How much sort of practical advice is going to be in that? And I guess maybe this sort of goes to the sorts of things you were just saying. I think the comments that were mentioned include things like construction speed and false work time and stuff. Is it going to be a how-to in terms of, well, these are the steps you need to take and here's some practical guidance to doing each of those steps, or does it just sort of set the bar where you need to get to and let people try and work out how to get there by themselves?
It's a really good question. Again, it's a bit of a mixture, to be honest. It's the LCCG is a collective of various parts of the industry and therefore has different sort of takes on different things. It should provide some practical advice, but also will give some, you know, links and references where more advice can be found. The strike time issue that someone mentioned, there is already guidance out there, and we can send something later on to try and help with that. So it's a bit of a mixture. There should be some really good stuff in there, depending on where you're from in the industry, because it's not just about engineers, it's about the wider industry. But certainly there'll be a need to go and look around other places as well to get more in-depth information at times.
And how ambitious is this guide? I mean, is this going to sort of set out how you can get down to net zero, or does it just set out how to get better today? What's the sort of time frame that it's looking at?
It's a bit of both, actually. So the various parts in the industry have set out their own route maps to get to carbon zero by 2050. Most of them tend to rely heavily on CCSU. So we've not necessarily gone down that route, but we've looked at different things that can be done today to bring it down, because, you know, the things we can do right now to bring it down straight away, and also looking at some of the newer technologies that might come in the future and how they might fit in as well. So it's looking at the next 30 years and trying to provide some guidance and advice as to how we can bring down our emissions associated with concrete today, and also some of the things that may have to happen in the future. But the idea is that we're going to try and update this as well, because one of the things we're looking at is trying to baseline or benchmark where concrete is today as well, because that's also quite a challenging thing to do.
And Matthew, I guess a sort of similar question to you. I think somebody actually asked the question of, you know, how could steel production ever be absolute zero emissions if we can't get carbon capture to work? So again, do you want to comment on the sort of time scale that you're thinking at? And, you know, that second graph you showed where everyone was down near zero, is that a sort of ambition, or is that something you expected to try and push people towards?
Well, it's certainly something we have to push people towards. I think it's a really good question about carbon capture and storage. I think there's a few sites who are I suppose, resting on the assumption that it will work. And I would agree with the question, what's behind the question, it's fairly uncertain. If carbon capture and storage isn't working, then you're really looking at hydrogen and direct electrolysis, or an awful lot of offsetting. And I would say it's the first two of those. You know, one can only offset what cannot be otherwise removed. And so I think if one's looking at, you know, natural gas and coal and then carbon capture, and then if carbon capture isn't working, you're actually looking, I think, at those other technologies. You're looking at hydrogen, you're looking at direct electrolysis as alternatives. I think that would be my view. And incidentally, biocarbon also as an alternative. Sort of.
Yeah. Okay. Well, I want to go back to timber as well, because I'm aware we're going to end up spending the whole time talking about concrete and steel. Will, thank you again for sort of like laying out so clearly the difference between biogenic and fossil carbon, what that means, and how you should sort of pick up on a few of them. We had a couple of questions in as we went, which I think, whilst the people asking them were brave enough to ask, I'm sure there's others sort of thinking as well, particularly if it's the first time people have thought about this topic. So, you know, there was a comment along the lines of, if I design for reuse, at end of life, isn't that going to mean that my embodied carbon's negative? And there was another comment around modules C and D, the emissions being written down, looking like maybe they encourage you to incinerate at end of life, or the way I might think of it is that they don't necessarily encourage you to reuse on a purely sort of carbon number point of view, because as you put it, this always leaves the system regardless of what. Do you have any comments around that sort of idea of, designing for end of life, what it means in terms of your carbon numbers, how we can encourage more of that?
Yeah, I think mostly the way that module C and D is treated in the standards, it works. If you're recycling your timber, then you should be claiming a negative module D because you haven't had to manufacture something from new. You also include the manufacturing emissions if you're turning a timber beam into some chipboard. The process of chipping it and gluing it back together again, it gets included in module C as well. So it's all consistent, except for, as somebody has highlighted, the fact that if it goes into a new product, you're losing that biogenic carbon to a new product system. I think that's another argument for keeping them separate when you're explaining that, because then it's more easy to say that, okay, my biogenic carbon is leaving my system and it doesn't get muddled up with the fossil emissions that are being treated differently. If you want to get around that, I think one of the potential problems is perhaps if you recycled something into MDF or some packaging or some animal bedding, that carbon, the biogenic carbon, is not going to hang around very long. Whereas if you reuse it in a timber building, it probably is going to hang around a long time. And the only way that you can properly capture that is by doing 2 life cycle assessments together for your building and the one after it. That's the only way I can think of where you could properly communicate those benefits. So in that case, I don't think it would be too hard to do that, as long as you're open and transparent to say that this is what we hope will happen and isn't necessarily what is guaranteed to happen.
Yeah. I completely with you. Since you started sort of explaining, just treat them separately, biogenic and sort of fossil, it does make the conversation easier, because then you're talking about real emissions that we are having today, and we know we are having because we're turning a tree into a building, say, versus this sort of the unseen bit, which is to do with capturing it, hiding away, which has benefit, letting it back out, what happens next. Yeah, my personal view is anything to do with end of life as well, there's always going to be a bit of sort of guesswork and gambling. So if we can maybe focus a bit more on what we can definitely control today, that would be a good starting point. We had a specific, well, a couple of really specific questions for you as well, if you wouldn't mind answering them. So one of them was on the graph you showed, which looks at steel versus concrete versus timber, and obviously on the timber graph, you looked at the sequestration and you'd use your forward-looking approach for that. The question was about the concrete one, actually, and it was whether or not you accounted for the impact of concrete carbonation within that, and maybe if you know a bit about the sort of scale or orders of magnitude that might exist for that, you could share some of that with us. That would be quite interesting to hear.
Yeah, definitely. I'll have a go. So those 3 graphs were based on the entire building. So the timber one includes a lot of concrete that's in the foundations, for example. So it's not just material comparisons, those are building comparisons. The numbers were generated using the iStruct's fantastic how to calculate embodied carbon guidance. So based on that, I did account for the carbonation of the concrete at 2.5% during the lifetime, and then an additional 5% at end of life. Those are obviously quite rough and ready predictions, and as concrete people will know, the amount of carbonation happens is very, very dependent on the cement that you've used and the surface area that's exposed to the atmosphere and how long it's exposed for. The difference, I think, between carbonation and sequestration in timber is that the amount of carbon dioxide equivalent stored in timber is actually more than the mass of the timber. It's about 1.5 times that mass, whereas the maximum amount of CO2 that you can recapture in concrete due to carbonation is the limit is much less than the mass of CO2 that was emitted in the first place, because it's only those process emissions. So the magnitude is inherently going to be different. That's another key difference, I think. You get more back from timber. And obviously the other difference is also the timing. So you're putting the carbon out and then recapturing it for concrete, whereas for timber, I mean, you can argue it either way, I guess.
Yeah, okay, I think that's clear. I think we've got, in theory, we're about to go onto a break, but I've just got one more question to ask Paul, if that's okay. And Paul, if you want to comment on what Will just said as well, please feel free to. We've had a couple of questions about sort of alternatives. So you mentioned GES, but obviously there's other cement replacements as well. And somebody also asked about, graphene instead of steel rebar, for example. And again, there's, other products are available too. Do you have any sort of closing comments on use of other alternatives? Do they sort of fall into the same messages you already told us? Or are there other things to look out for out there? Anything we should be aware of, such as the products mentioned?
Yeah, so trying to tackle those in turn then. So alternatives, yes, there are other ashes available. They need to obviously be at the right scale and meet the necessary requirements. So that's a key challenge with any kind of alternative stock, is making sure it's consistent in quality and that you're not going to end up with a poor quality concrete, because clearly if it fails later on, that's not going to be acceptable and it's going to waste more emissions. I think, as I said earlier on, that we need to sort of embrace a broader range of cements, and depending where you are in the world, there'll be different suppliers for different things. And it may be that we need to start being more localized in terms of what we can use as a supplementary material to CEM 1, or indeed to replace it entirely. So definitely lots of other things there, but there'll be other requirements for them to be used. In terms of graphene, I can't say I'm familiar with the use of graphene directly, but more generally speaking, certainly we need to look at other things instead of just rebar that we've always used. So even simple things like using steel fibers can make a big difference. And a colleague of mine did some work on that and found that replacing mesh reinforcement with fibers would save around 25% of the weight of steel. So, really simple thing to do actually, and that's also quite well established. But the contractor didn't want to do it because it was too novel. But we need to be testing these ideas, and certainly things like graphene or other fibers or any other kind of additives, we need to be seeing if we can use them. And also using higher strength concrete may work overall if it reduces the amount of concrete. So there's a really broad picture to look at for your projects. In terms of carbonation, I think I'd probably largely agree with Will. It's very dependent on the particular project, how much availability of that concrete there is to the air, and what the actual carbon dioxide availability is within that air. But the key thing for me is the timing, and that is that with our production of cement, it's out there already. If you buy a bag of cement today, it was emitted months ago already. It's in the air. The carbonation will take decades, possibly, to the end of the century, depending on how that building is used. And so I don't think it's something that necessarily we can use as a means to justify any kind of more release of carbon today. We need to focus on getting that carbon release down today, and then the carbonation effect is a good thing to have, and may well help us long term to bring back the carbon dioxide level to a more normal rate. But right now, I wouldn't necessarily argue it's something we should be using as an advantage.
Yeah, thank you. Look, I should let you all go because we said we'd only keep you till 20 past. Thank you again to the three of you for giving up a bit of time this afternoon, or I think you all this afternoon. I know that at least one of you is currently on holiday, so extra special thanks. We're going to have a quick break now. It's usually 10 minutes, but it's only going to be 5, but there you go. Hopefully those questions were interesting enough for you anyway. So please join us back at 4:30, where we're going to move on to some sort of broader carbon things. We're going to talk about carbon on site and then carbon in bridges. So see you all then, and thanks again, Will, Paul and Matthew. Thank you.